and chemcracker. Today we're looking at the equilibrium law. The equilibrium law establishes a relationship between the quantities and or concentrations of products in an equilibrium reaction relative to the quantities of reactants. And what it says is that at a certain point at equilibrium, there is a set ratio involving the products concentrations and the reactant concentrations. Let's look at it. Right, now for a reaction A plus BD equals CC plus DD, the equilibrium constant, which we call Kc, gives the product of the concentrations of the products raised to their stoichiometric coefficient. In other words, the product of C and D raised to their stoichiometric coefficients divided by the reactant concentrations A and B, the product of those, raised to their stoichiometric coefficients. That's A and B. And this is at a given temperature. Now let's consider the equilibrium constant for two equations. The first equation involves a reaction between nitrogen and oxygen to produce nitrogen dioxide. Now remember that Kc is the product concentrations, the multiple, that's the product of the product concentrations raised to their stoichiometric coefficient, right? Over the product of the reactant concentrations raised to their stoichiometric coefficients. Now, in this case, we only have one product. So we're going to put it there, NO2, and it's going to be raised to the stoichiometric coefficient, which is 2. And that's going to be over the reactant concentrations, the product of the reactant concentrations, which are N2 and O2 gas. And the stoichiometric coefficient for N2 is 1. Now we don't have to put 1 there because N2 to the 1 is the same as N2 in square brackets. And for oxygen, 2. But we don't need to put 1, we can leave it because N2 square brackets to the 1 is the same as N2 square brackets. So that is my expression for the equilibrium constant for the first reaction. Now, let's look at the second reaction. Now, in the second reaction, I also have one product, and that is ICl3 gas. All right? So that's for 1. Now, for 2, right, Kc is going to be equal to the product. This time, the product is ICl3. And the stoichiometric coefficient again is 2. And we have 2 reactants, iodine, which is I2. Stoichiometric coefficient is 1. We don't need to put that. We can put it if we want. And Cl2, stoichiometric coefficient is 3. So there we have it, the equilibrium expressions for 2 equations. Now let's work out the units for the equilibrium constant Kc. The unit for Kc will change depending on the expression. So what you want to do is to fill in the units for each concentration term and then cancel it down to get the final units. So let's look at this one. Now, square brackets usually means concentration. And so the concentration is usually in mole per dm cube. So what I'm going to do is just fill in those terms right here. So I'm going to put mole per dm cube, which would be that. And of course, that's squared over this, which is mole per dm cube, times, this would be mole per dm cube as well, but that's squared. Now, if we cancel it down, that into that is 1, and that into that is 1. So that would be 1 over mole per dm cube. And then if we invert the mole, that becomes mole to the minus 1 and dm cube. You can put the dm cube before, you can put mole behind, doesn't really matter, as long as you get it right. Consider a heterogeneous system. So far, we looked at two systems that contain only gases. So therefore, that was a homogeneous system. All the reactants and products were in one phase. Now let's consider a system where you have reactants and products in different phases. For example, this reaction, in which two gases are formed from a solid. Now, in such a system, we must remember that the concentration of a pure solid or a pure liquid remains the same. It does not change during the reaction. So, therefore, their concentration is a constant throughout. Now, what does that mean? Now, Kc for this system, Kc will be equal to the product's concentration raised to the stoichiometric coefficient, which is 1, over the reactant concentration. Right? It's solid. Though. Now, because this is a constant, right, we can incorporate it with that constant by just multiplying these two, right, and make it one big constant over here. Right? And this now becomes a new constant, Kc. Alright? So essentially when we write the equilibrium constant for heterogeneous systems, we ignore the solid terms or the pure liquid terms. We just use the terms which are gaseous or aqueous.